Hello and welcome to Full Tech Ahead. I'm Amanda Razani and I'm excited to be here today with Rick Ward. He is the founder and CTO of OrbitsEdge. How are you doing today?
I'm doing great.
Can you share a little bit about your background and what led you to OrbitsEdge and what does OrbitsEdge do?
Okay, so sure. I got my first space job in 2016, and that was working for a company called Deep Space Industries. And they were working on asteroid mining, which I did not even realize was a real thing a year before that. And the company pretty much ended in about 2018, which revealed that it probably wasn't actually a thing yet. And I wanted to solve some of the technical infrastructure problems that I felt were prerequisites for that capability. And one of the big ones that I wanted to address was autonomy. The classes of computers that we historically take to space are, 10 to 20 years old, older than what is commonly used here. And I felt that we're either never going to get to autonomy with that architecture, or we'll do it in like 2050 and it's going to be it'll be too far out for it to matter for me. So I wanted to come up with a way that we could fly modern computers in space. And that's what OrbitsEdge is about.
Wow. Okay, so flying modern computers in space. What's involved in that and where are you in this process right now? Can you give me some idea?
Yeah, so first off, there's two problems. Well, there's more than two problems, but we'll reduce it to two. There's the radiation. So you've got a radiation environment in space, obviously, and that's going to be different depending on where you're going in space. If you're going to low Earth orbit, it is one of the more hospitable places in our solar system. If you go to geosynchronous orbit, there's a great deal more radiation there. If you go to the moon, there's more and different types of radiation in lunar orbit than there are around right in Earth orbit. If you go to Mars, you go to the main belt, you go to the gas giants, and you have very different radiation environments there. So first, you have to come up with a way to do physical radiation shielding. What has historically been done is rad tolerant hardware, which is viable, but it gets so much more complex once you get into more modern and more advanced compute hardware. So if you can do shielding to reduce the radiation that actually gets to your boards, then that's hugely helpful. The other big thing that we're doing is there's some software mitigation you can do. So there's things you can do to make things more fault tolerant. Then the other thing that we're doing that we started recently, and it's progressing well, we're looking at unrolling it next yearish, is get into board design. If we design our own board, then we can incorporate radiation tolerance at the board level, and we'll have a much more viable solution then. So we can have a combination of shielding, board design, and fault tolerant software. So it's really going to be a multifaceted approach. The other aspect to it is thermal management. When you're working with small computers, your thermal management it's a pain, but it's more manageable as you scale up. So our first computer is going to be 10 watts, so very, very small. As you scale up into 20 some odd watts, you have to get into active thermal management systems. As you get above, say, 1,000 watts, now you're getting into a point where you have so much thermal density that you have to have like deployable radiators that fold out. So your thermal management problem gets more complex as you scale up, as you get bigger. Once you get big, then 90% of your worry is about thermal management as opposed to radiation. So yeah.
Wow. So I imagine there would be a lot of benefits to being able to have this technology in space. What are some of the opportunities that would be available if you can work through these challenges and get this up into space?
So we're looking at three primary markets for our initial computer. And I mentioned it's 10 watts, so it's very small. It is quite modern. We're actually going to be doing about 15 trillion operations per second of computing power. Once we do our own designed boards, we'll be doing about 65 tops, that's referred to as, for the same power budget for 10 watts. So we're looking at really modern, really powerful stuff for what it is. So we've identified three primary markets for this onboard compute, and we're calling them kind of now, near, and next. So the now is Earth observation analytics. The idea there is to put the computer on board EO satellites so that we can do some of the analytics that's typically done on the ground, do it in space. There's also some things that we can now do that would be otherwise impossible because you have the data right there at your fingertips. The big issue with EO has historically been, well, with all space things, has always been the transport layer. We're much better at capturing data than we are at transmitting it down to the ground. So we have serious bottlenecks in getting stuff down to the ground. So if we can consume some of the data at the point of origin, then we'll be able to clean it up. One of the big things that we say is for EO, what the end customer is actually looking for is needles. And what we're doing is we're taking haystacks, loading them on semis and shipping them across the country so that we can look for the needles. So if we can go ahead and pass a magnet over those haystacks, then we can go ahead and find a lot of those needles, send the needles down, and then worry about the haystacks later on. So that's the now. The near is something called remote proximity operations. So that's RPO. Basically, it is maneuvering. Whenever a spacecraft has to maneuver to another spacecraft. So if you want to do refueling, servicing, inspection, assembly, all of those things involve a spacecraft going to another spacecraft, doing some work in that vicinity, and then going away and doing other stuff. So if we can provide autonomous agents to enable RPO, that will help a lot. Right now, that's typically done through direct command control. So basically, it consists of a lot of commands sent to the spacecraft over a long period of time. And you can do that. You can get away with that if you're going to do it once or twice a year. But if you get into doing it once a week, now it's getting prohibitive. So if we can break that down into a series of agents that each one moves through a permission type architecture. So let's say we break it down into 6 agents, and you go from 20 kilometers away to contact over a period of 6 agents. The first one does its part. When it reaches close to the end of its overlapping area of responsibility with the other one, it says, hey, this is where I am. This is where I expected to be. Can I continue? And if it doesn't receive a yes, then it will stop or do some other process. If it receives a yes, then it will just hand over to the next agent, and the next agent will take over the next portion and repeat the process. So that's the idea behind enabling RPO. The next one is in-space manufacturing. So that's ISM. And there's some really cool stuff that can be done with that. The big thing that I've been harping on for like 4 years, is crystallography. So when you form crystals on Earth, there are certain imperfections that occur due to things settling, due to gravity. If you can do that same process in space, then you're not going to have that sort of settling effect, and you can have much more perfect crystal formation. And we're actually talking with companies right now, a couple of companies that are doing biopharmaceuticals. One company is focused on protein synthesis, so protein crystal synthesis. They're very interested in this. Another one is focused on cell growth. And honestly, both of these tasks are procedurally very similar. They're both going to involve effectively somebody looking through a microscope, which can be done with a vision-based AI agent. And they're also going to involve different types of telemetry, things involving maybe temperature, salinity, electrical conductivity, various things of this nature. And it's going to be a combination of those telemetry readings as well as what it looks like that will guide the process. And we can help provide that through a series of AI agents.
So the environment in space is a better environment to conduct these experiments.
Yes, and it's not just about the experiments. Once we figure out, hey, we can do this once, now let's do it 1,000, 10,000, a million times. And that's getting into a full-on space ecosystem that's used to produce. So I mentioned crystallography specifically. So that ties into a lot of different verticals. So I mentioned biopharmaceuticals, so crystal growth, protein crystals. Then the other big ones are things like metallurgy, ceramics, optics. So you can make optically pure crystals for optics. And that can be either lenses or mirrors or fiber optic cables. That's one of the big things that's happening. The material called Z-bland. And another thing that you don't necessarily think about is the silicon chips we use are made out of a crystalline wafer. If we can produce those crystals in space, then we can get higher quality on the output wafers. There are also certain processes in the silicon chip manufacturing that involve step one, grow a crystal. And if we can do those in space, and there's other things that benefit for chip fabbing, but just in terms of crystallography, there's multiple steps we can do in space that would yield better results than we get on Earth. And for some of the metallurgy stuff, there are alloys that we would simply not be able to create on Earth that we could create in space. Because one of the issues is if you have a liquid and you have one thing in the liquid that is high density and the other thing that is low density, they're going to want to separate out before they solidify. So if you go into a place where there's no gravity, then they won't separate out and you can keep them at the desired concentrations.
That is so interesting, and I'm glad you shared the use cases because that would have been my next question is why do we need perfect crystals, you know?
And
So
why do
I
we need
appreciate
perfect crystals?
Yes, lots of reasons apparently. So eventually down the road, would this be cost effective for companies to send this stuff up into space to create?
Inevitably so. So one of the aspects is doing things that are simply impossible to do here on the ground. So now you're saying, well, the comparison is have it or not have it at all. So that is the first place you would start. The second place is have the same thing but better quality. That is the next place to start. So when you're making silicon chips, what you start off with, you think of the wafers. You may have seen the wafers. They're like 300 millimeters, about a foot across in diameter. That actually starts from a big ingot of silicon, which is drawn out through a process. And the ingot is like over a foot in diameter and 1 to 2, oh, sorry, what is it? 3 to 6 feet long. So that is a big hunk of crystal. And then they basically take that down, they turn it, they slice it and dice it, and you end up, well, dicing is actually last. They slice it and end up with wafers. Then those wafers get polished. So any sort of imperfections in those wafers, in the crystal itself, will manifest in whatever. So if there's a flaw, it goes through the length of the entire ingot, then that flaw is going to be visible in hundreds of chips across those various wafers. So you make your disc, you make your wafer, and it's got that flaw right here. And then the other wafer that you make just above it has the exact same flaw in the exact same spot. It's going to be like you've got a split in a tree, and then you make a series of tables out of that split out of that tree. Well, you're going to have those same flaws in all those all of those. So if you can make that more perfect without those flaws, then you're going to have a much higher success rate. So the last step you do when you make a chip, so you've got your wafer, you've got all these chips. Then they do what's called dicing them, which is basically like how you cut the round disc into squares, and you get all the little chips off of that. So now you have like one little chip that's 1 centimeter across roughly, and you've got a bunch of those out of the 1 foot diameter disc. So you've got all these, you run them through tests. So you have this disc with hundreds of little chips on there, and you separate them out. Then you grade them all. Basically, you check to see how well they work. And based on how they work, they go into either the reject pile, which doesn't work well at all, the works okay, which basically goes into the discount bin. They're still usable, they're still decent, but they're not going to be fantastic. So we're going to get what money we can out of them. And then you've got the high grade bin, which is, hey, this one's great. It's high purity, high quality, and we're going to sell this one for the premium price. And this is what pays for the whole thing. If we can grow things that are more optically pure, we can reduce those first two bins and have more of the stuff total being high quality. Additionally, there's various things of when you're manufacturing something, you have to allow for tolerances. So you can only make your design and your process so precise because you know that you have a little bit of slop in the product, in the initial product. Well, if you can reduce those tolerances, now you have room to make a less tolerant design. So there's a lot of really cool stuff you can do with that in terms of making something fundamentally better than what you could do without it.
Wow, there are so many solutions that could potentially be solved within the aerospace industry that I had not thought about before.
Oh, yeah. There's so much. And then one other aspect is launch cost. So we just saw for us, I guess this was day before yesterday, Monday, wait, whatever it was. For us, we just recently saw the successful 10th Starship launch, and it landed the way it was supposed to in the water, but where and when it was supposed to. So it was really impressive. That has the promise to knock a zero off of the cost of launch, which is going to be absolutely huge. There's a lot of these business cases where any business case, you think about it, above X cost, it doesn't work, and below X cost, it does. It's kind of like saying, if the cost of a cheeseburger was infinite dollars, the demand for a cheeseburger would be zero. Whereas if the cost of the cheeseburger was zero, demand would be infinite. So you kind of need to figure out like where that sweet spot is from a business side, but above X, it just doesn't work. You just don't have sufficient demand to stay alive. So that's what we're looking forward to seeing. One of the things about space has been historically, we love messing with photons. We love messing with data, things that can be transmitted. We hate messing with atoms because atoms have to go up and they have to go down, and you have to keep them in the same shape on both of those processes. So now we're getting into the point where we can start messing around with atoms, and that's going to be pretty wild.
Wow. Well, and we hear that there's soon to be mission to the moon, and there's this ambitious goal for Mars as well. We certainly need computers up in space that work properly and
Yeah.
can provide high levels of value to be able to transmit back to Earth and to do all the projects they're talking about doing, especially on the moon.
Yeah, one of the big things I've been saying for some time is there are two primary drivers for autonomy. One is latency, meaning distance. And it's not just a matter of latency, it's also a matter of like how much comm gear do we have to send back all the stuff we're generating. So one of the problems with the moon is we're already overwhelming the communications networks back to the ground, back to Earth. So if you could kindly not send, 4K video back home, that would be great. So you've got latency, and the other one is complexity of operations. So if you have something that you need to move it once every 24 hours, yes, you can do that by command line. You can do that by, explicitly ordering it to do it and telling it how to do it and all that stuff. But if you've got something that's going to be moving much faster, doing more complex stuff, then it really breaks down. So if you've got like a mining robot that's picking up lunar regolith, it can't move at a speed of meters per day. It has to move kilometers per day. And there's just so much that can get so much trouble that a little truck can get into, a little robot truck can get into with like a second of time lag. You can do a lot of bad things. And then you toss in, well, it's not one truck, it's going to be like 20 trucks. And they all have to move together and they all have to do the same or similar but different tasks, all in conjunction with each other. It just gets too much. And 20 is too much to have, 20 human drivers on site or on the vehicles. So you really do have to have a thing where they do a lot of the work themselves, and some human, preferably local, is in the area as a supervisor over a swarm rather than either in the driver's seat running around and bumping on the craters, or even in a shirt sleeves environment on the base. It's going to be tremendously expensive. One stat we have right now is ISS astronaut time runs about $130,000 an hour. So I can't imagine lunar astronauts are going to be cheaper than that.
No.
So the less of their time you can consume, the happier you'll be.
Absolutely. Well, if there was one key takeaway you could leave our audience today with, what would that be?
The future is now, old man. I don't know. The big thing I would say is the environment we're seeing has to be kind of like what the 1960s had to have felt like in terms of space. We have so much happening right now, so much is going on. It's really hard to see it from it's hard and super obvious and easy to see it from the inside because it all happens every day. But if you step outside and say, well, what have we done with reuse in terms of Falcon 9, for instance? Not as much as I would have liked to have seen so far. And part of that's because costs have been relatively static. People haven't really figured out that it's a different paradigm yet. So one thing is we've historically built spacecraft as one of one or one of maybe three. And with that attitude, that mentality, you're basically saying my prototype has to work perfectly, which means there's going to be like a dozen sub prototypes on my shelf or in the scrapyard to get to that point. And then I know that I'm probably never going to do this exact project again. So there's a lot of optimization that can't happen. There's a lot of optimization that has to happen in terms of making the darn thing work properly, perfectly, first time ever for a 5 to 10 year mission life, maybe a 10 to 20-year mission life. So you end up going super conservative on everything. And then you have the additional constraint of launch is expensive. So you basically have like a Formula One race car ethos. If there's a gram you can take off, you take it off. If that means you have to go through lots more computational analysis for stress and strain, then you just do it because it's a gram. Like, we're talking grams here, people. Once we get to much lower launch cost, it's going to change the way we do stuff. It can change us from a Formula One race car to a Honda Accord, which doesn't sound nearly as sexy, but it's it's so much more economically feasible because now I can change my attitude from I'm making one of one to I'm making one of 50. And I can evolve the design over time. And it's not just about evolving it to be better, but I can evolve it to be faster and cheaper to produce. My materials list is not now the now my materials list is no longer like, do I do carbon fiber, titanium, or aluminum? Now it can be like, what if I do steel? And there's a lot of things you can do. What if I do stamped steel? There's a lot of choices you can make that would have been unfeasible, unthinkable. Like, think of the grams. Well, I don't have to think about grams that way anymore. So there's a lot of stuff you can do. Can I design my spacecraft? I was talking with somebody the other day. Can I design my spacecraft so that the components could be sold on a secondary market? Like, that is absolutely unheard of in a world where every single component is a one-off and bespoke. So there's a lot of ways we can look at the world that just don't make sense today, but they will make sense before too long. And the products of going to space will be much more attainable for people. We can produce these crystals for pharmaceuticals. We can produce things with much lower variance, much higher probability of the thing that you get is the thing that you want, which should reduce interactions and side effects and things like that. Plus, we can make crystals that are otherwise impossible to produce here on the ground. So there's a lot of things that we can do with this, things that will actually affect human lives, not just in terms of, drugs that save your life, but other things that just make life more convenient. I mean, what's the market for GPS? In how many ways does GPS touch your life? It affects your life in how the pizza gets delivered to your house and how the shipping containers make it from wherever they start off to wherever they end up. So we've got some truly remarkable space technologies that just kind of faded into the background of our consciousness, but they're there every day and we couldn't live without them at this point.
Yeah, absolutely. Well, technology is advancing quite rapidly, as we know, so it'll be exciting to see the future, say 5, 10 years from now, what happens.
Absolutely.
Well, thank
Yeah.
you so much for coming on the show and sharing your insights with us.
Thank you. I enjoyed it. It was a good conversation.
Absolutely. And thank you to our audience. Stay tuned. There's more podcasts coming up.